Morning. Hope you guys are all doing well. Thanks for listening to this lecture, and we'll go ahead and get started. If you remember last time, we were looking at buffers, right? Remember, a buffer contains an acid, a weak acid and its conjugate base, or a weak base and its conjugate acid. All right. And last time we learned that you can calculate the pH of a buffer using the Henderson-Hasselbalch equation, right? pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. Okay. And these are the initial concentrations. And remember that this came from working an equilibrium problem, right? So this is just a shortcut to working an equilibrium problem with a common ion. Okay. And of course, it can only be used when the X is small approximation is valid, which is true for the vast majority of buffer systems. All right. So today we're going to look at how you calculate pH changes in buffer solutions upon addition of an acid or a base. All right. So if you have a buffer and you add acid or base to it, how does the pH change? And what we're going to see is that these calculations involve two parts. The first part is a stoichiometry calculation. Remember last time I gave you a couple equations for how a weak acid in a buffer neutralizes a base, or how a weak base in a buffer neutralizes the acid, right? These equations are the number 3 and number 4 equations of the ones that I told you that are going to be very important going forward. So let's just review those. Remember, a weak acid neutralizes an added base by forming H2O plus A minus, all right? And a weak conjugate base neutralizes an incoming acid by forming H2O plus the conjugate acid of that weak base, right? So those are our two equations for neutralization. And remember, for these two equations, we're going to work in moles. All right? Okay, so let's see then. Let's have an example. So we want to find the pH of a buffer that is 0.1 molar. So let's just write this down. Example. You have a buffer that is 0.100 molar acetic acid. Excuse me for a minute. Let me just. The buffer that's 0.100 molar acetic acid and 0.100 molar sodium acetate. Okay. And pKa, it's not on the slide, but pKa for acetic acid is equal to 4.75. Okay. And you're going to add, so you want to add 0.010 moles of NaOH, and then find the pH after the addition, right? So the first thing to remember, let's just review really quick. What is the initial pH of this buffer? We just plug into this equation. Log of the concentration of the base, right? The base in this case is this guy. And the acid is this guy. So the pH, since this is equal to 1, log of 1 is 0, the pH is just equal to pKa, which is equal to 4.75. All right, now what happens when I add the 0.010 moles of NaOH to it? Well, remember, this is going to react with one of the two buffer components, right? It's going to react with, since this is a base, right? It's going to react with the acid, okay? So out of these equations, which ones are we going to use? Which one are we going to use? Number 3, right? We're going to use this equation because there's the base reacting with the acid. So let's write that down. So if we first do, this is the stoichiometry calculation. All right, and we write down the equation for the acetic acid reacting with the strong base and neutralizing some of it, right? To form H2O plus the conjugate base, right? And now for the stoichiometry calculation part, we're going to make another table that looks a little bit like an ICE table, which we've made in the past for equilibrium problems, but it's not an ICE table. Okay, it's a stoichiometry table. And on that table, we're going to have 3 entries. We're going to have before, what are the moles before the addition, right? What did we add? And then what were the moles after the addition, okay? And because this has this little acronym BAA, I'm going to call these BA tables, like the sheep, okay? So this is going to be called a BA table, not to be confused with an ICE table, all right? In BA tables, we're doing stoichiometry calculations. We're going to be using these equations up here, okay? And we're always going to work in moles. In ICE tables, it's an equilibrium problem, and we're always going to work in molarity. All right, so keep those things separate. All right, so what were the number of moles before the addition? Well, we had 0.100 moles of acetic acid and 0.100 moles of the acetate ion, right? And then in this line, we're going to put what we added, all right? So in this case, we added 0.010 moles of OH minus, all right? And now in this table, in this kind of table, we don't sum things like we do in an ICE table, but rather we say, okay, if I have 0.1 moles of acetic acid and I add 0.01 moles of OH minus to that, and it reacts stoichiometrically, right? How many moles of these things are left? Well, we know that 0.01 moles of this is going to react with 0.01 moles of that, right? So that leaves us 0.090 moles of acetic acid, right? After the addition. And then, of course, this gets neutralized. So that goes to close to 0, although we know it's never exactly 0. And at the same time, as this gets neutralized, it forms some of the conjugate base, right? So how many moles of the conjugate base do we end up having? Well, we have 0.1 moles there originally, plus the 0.01 moles that formed from the reaction, right? So that's going to give us 0.110 moles. Does that make sense? Okay, so now notice what we have. We have our new amount of acid and conjugate base, right? So now we can plug back into the Henderson-Hasselbalch equation in the second part. So the first part is the stoichiometric calculation. The second part is the equilibrium calculation. But for the equilibrium calculation, because we have a buffer, we're going to use the Henderson-Hasselbalch equation for that part of it instead of drawing an ICE table. We could do the whole ICE table thing and calculate it out, but that just takes a little bit extra time. And since we're going to be doing a lot of these, we're going to stick with this method where we just use the Henderson-Hasselbalch equation. So the pH is going to be equal to the pKa plus the log of the concentration of the base over the concentration of the acid. Now notice in this equation, since it is an equilibrium calculation, it uses concentration, okay? In this problem, we're told that we have 1 liter, right? So we could divide these both by 1 liter and find that, you know, this is 0.11 molar and this is 0.090 molar, right? But notice that because the volume is in both the numerator and the denominator, it cancels out. So the nice thing about the Henderson-Hasselbalch equation is because these are in the same solution, all right, for this equation, you can work in either moles or molarity, okay? Either one works for this equation. For normal equilibrium problems, always work in molarity, okay? Never in moles. But for this Henderson-Hasselbalch, we have the freedom to do either one. All right, so then I'm going to put in the 4.75 here plus the log of 0.110, the concentration of the base, right, divided by 0.090, concentration of the acid, right? And that's going to give me a pH of 4.83. All right. So notice the pH was 4.75, right? I added some base and the pH went up to 4. Oops, sorry about that. I got to bring that up a little bit. And the pH went up to 4.83. Whenever you work these problems, remember, develop your chemical intuition, right? You develop your sense of what should happen, right? If I add base to something, what do you expect? Will the pH go up or down? Well, since you're adding base, right, you expect it to go up, but this is a buffer system, so we don't expect it to go up dramatically. And in fact, what we see is a small pH increase, right? Because the buffer is working, doing its job, right? And so you only see a small increase in the pH, okay? Now, what would happen? We just saw, right? This is the example we just did, right? We have acetic acid, we have the pKa, and we saw that the pH went from 4.75, right, to 4.83. What would happen if we added the same amount of base to pure water? Well, how much would the pH change? Just so you can see the effect of buffer, right? So pure water, let's say, if it's really pure and has no impurities in it, we'll have a pH equal to 7.00, right? Now, what happens when I add 0.01 moles of NaOH to pure water? Well, all of a sudden the OH minus concentration increases to 0.010 molar, right? And we know that the pOH is 2, so the pH is 12, right? So the pH jumps, so we add 0.010 moles of NaOH, right? And the pH jumps from 7 to 12, 5 pH units, right? So compare that jump in a non-buffered system. When we add the same amount of base to a buffered system, such a small pH change in comparison, right? So that just tells you how a buffer works, right? And it gives you a sense for how pH changes in buffer occur. Okay, normally if this was a real lecture, live lecture, I would ask you a learning catalyst question here. I still want you to interact. So I'm going to give you a minute to answer this question here, and then we'll move on, okay? So go ahead and try to answer this question. If you want some more time to think about it before you answer, go ahead and pause the video here. Otherwise, I'm going to reveal the answer, all right? Pause the video if you want more time to think about it. Otherwise, I'm going to reveal the answer. All right. The answer to this question is B and C, right? If you add HCl to this buffer, right? So you're adding HCl to a buffer that is sorry, get this straight. So you have HF is the acid, right? F minus is the conjugate base, and you're adding HCl, right? So what's going to neutralize the HCl? The base, right? The base. So it's going to react with the base. So the reaction, right? If we go back to our equations, right? We're adding acid, right? So it's going to react with the base, and that's the equation we want, right? So it's going to be F minus plus H3O plus, right, goes to form water plus HF, right? So notice what will happen if I add HCl, F minus will decrease because of that reaction, and HF will increase, okay? All right, another question for you to try. 1 liter buffer is composed of 0.1 molar HA and 0.1 molar A minus. Calculate the pH upon addition of 0.022 moles of HCl, and it gives you the pKa. So again, I'm going to pause here and give you a minute to work this out. So go ahead and do that. And then I'll reveal the answer. Okay, you might need more time to work this one out. I don't want to have a big blank space in this video, so I'll just ask you, if you haven't finished working it out yet, go ahead and pause the video here, finish working it out, and then restart it once you're done. All right, give you a second to do that, and then I will work out this problem. Okay, for this problem, right, again, you have 1 liter of a buffer. And it's 0.10 molar HA. And because it's 1 liter, that means you have 0.100 moles of HA, right? And you have same thing, 0.10 molar A minus, which means you have 0.10 moles of A minus, all right? So remember, with these stoichiometry calculations, you always want to work in moles. And it's saying here that I'm add 0.022 moles of HCl, okay? So in the previous example, we added a strong base to the buffer and it reacted with the acid. In this example, we're adding strong acid, so it reacts with the base, right? So let's write out the neutralization equation. So remember, these calculations have 2 parts. The first part is a stoichiometry calculation. So the stoichiometry here is going to be A minus plus H3O plus goes to form H2O plus HA. All right. And we're going to set up our Baugh table. Before addition, addition, and after addition, right? And before addition, we have 0.100 moles of A minus. And we have 0.100 moles of HA, right? And then we're going to add what? 0.022 moles of H3O plus, right? So sorry, I didn't mean to put the plus sign there. That just means that's what we're adding, all right? And so what's going to happen here? This is going to decrease by 0.022 moles, right? So that's going to end up being 0.078 moles. This is going to increase by 0.022 moles. So this is going to be 0.122 moles, right? So then that's stoichiometry. The second part of the calculation is the equilibrium calculation. We're going to use the Henderson-Hasselbalch equation for that part. So pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid, all right? And so that's equal to 4.25 plus the log of, and again, remember here, you can use either concentration or you can use moles. Either way, it doesn't matter, because if you convert it to concentration, the volume would cancel out because it's a ratio of concentrations, right? So that's the log of 0.078 divided by 0.122, right? And if you work that out, that's equal to 4.25 minus 0.194, which is equal to 4.06. Now, notice what happened here, right? We added acid. The initial pH, right, since these were equal, was 4.25. Adding the acid had the effect of bringing the pH down a little bit, right? Just like we would expect, right? So always think about what happens. That's why this is negative in this case, right? It brings the pH down, okay? So the answer was 4.06, okay? All right, very, very good. So far we've been dealing with buffers composed of a weak acid and its conjugate base, right? And we've used the Henderson-Hasselbalch equation to calculate the pH. We can also use the Henderson-Hasselbalch equation to calculate the pH of buffers composed of a weak base and its conjugate acid. So for example, if you have ammonia, right, that's the base, and you have ammonium chloride, that's the weak acid, you have a buffer in which you have NH3 as the weak base, right, and you have NH4 plus as the conjugate acid, right? So you can still use the Henderson-Hasselbalch equation, right? So we could still use this equation to figure out the pHs of these kinds of buffers. And it's easiest to just use the same equation, but just calculate pKa for the conjugate acid. All right? So you can use the same exact equation, but just find the pKa for that conjugate acid. Remember that pKa plus pKb is equal to 14. So if you know one, you know the other. It's easy enough to get it. And just make sure you always use pKa here, always use concentration of base on top and acid on the bottom, and you'll be good to go. Okay? So let's just do a quick example. It's going to be pretty straightforward. What is the pH of a buffer that is, let's see, do I have this calculated somewhere? Okay, let me just work this out here for you on the screen. So what is the pH of a buffer that is 0.5 molar NH3 and 0.2 molar NH4Cl? So again, we're just going to use this equation, but we're going to need to get pKa, right? So usually what you can find is the pK or the K for the species that is not charged, right? So in other words, when you look things up in tables for this buffer system, you're going to find K for this, right? You're going to find KB. So here's pKb, but no fear, because you can get pKa from pKb super easily, right? So pKa is 9.25. And then to figure out the pH here, we're just going to use the Henderson-Hasselbalch equation, put in the concentration of the base, right, which is 0.5, 0.2 for the concentration of the acid, use 9.2 for pKa, right? And that's going to give us 9.65 for the pH of this buffer. Okay? Does that make sense? All right. Couple other quick topics. Buffer range and buffer capacity. All right. So the question is, if you have a buffer made of an acid and its conjugate base or a base and its conjugate acid, right, over what range is that buffer effective? All right. So let's look at two scenarios. We're going to look at the relative amounts of acids and bases, or the relative amounts of acid and base in the buffer, and the absolute amount of acid and base. And we're going to ask, how does that affect the buffer effectiveness? Okay. So here's a quick calculation. In this side on the left, I'm going to say I have a buffer in which I have exactly balanced amounts of acid and conjugate base. So I have 0.1 mole HA and 0.50 moles A minus. Sorry. The initial pH is 5. All right. And so then I'm asked the question, okay, what's the effect, right, of adding 0.010 moles of OH minus to this buffer? So I do my Ba table. I figure out the changes, right? So HA goes from 0.1 to 0.09. A minus goes from 0.1 to 0.110. I substitute that into the Henderson-Hasselbalch equation, right? And I find the pH goes to 5.09. All right. So when I have exactly equal amounts of the two buffer components, the pH increases from 5 to 5.09. That's a percent change of 1.8%. Now, let's go over here to this side. This is a slightly different solution. In this case, the total number of moles of acid and conjugate base are the same, right? They sum up to 0.20 if I sum them both together. But in this case, I have much more of the acid than I do the conjugate base, all right? In this case, if you use the Henderson-Hasselbalch equation to find the pH of this solution, it's 4.05 before you add anything. Now we're going to go ahead and add 0.010 moles of OH minus. Here's my Ba table. This goes to 0.17. A minus goes up to 0.030. And I figure out my new pH using the Henderson-Hasselbalch equation. And what do I find? It goes up to 4.25. So in this case, it went from 4.05 to 4.25. Still getting buffered, but notice that the pH change was much bigger here than it was here, all right? The percent change was 5% here, was only 1.8% here, all right? So what does that mean? That means that buffers are most effective when the relative amounts of acids and bases are fairly balanced, all right? The closer they are to one another, the better the buffer. All right, what about absolute amounts of acid and bases? So in this case, we have a buffer that is 0.5 moles HA and 0.50 moles of A minus. The initial pH is the same, all right? Now I'm gonna add 0.010 moles of OH minus. Here's my Baugh table. I plug in the new amounts into my Henderson-Hasselbalch equation, and now the pH only changes to 5.02, right? So from 5 to 5.02 when the amounts of acid and base are fairly high. On this side, I have a factor of 10 less acid and base, all right? So a more dilute buffer. When I carry out the calculation on this side and add the same amount of OH minus, my pH rises to 5.18. So from 5 to 5.18. Again, notice much bigger jump here than here, right? So the percent change on this side is 3.6%. So what does that mean? That means that buffers are most effective, right, when the absolute amounts of acid and conjugate base are higher, right? So the higher they are, the more effective the buffer, okay? So we can summarize this like this. A buffer will be most effective when the ratio of base to acid is 1. In other words, when this ratio is equal. But we're going to say that it's effective as long as that ratio is between 0.1 and 10. In other words, we'll say the buffer is effective if this ratio is 0.1, which means there's a lot less of the base than the acid, or 10, in which case there's a lot more acid than the base. As long as that is in this range, then we basically still have a buffer, right? But if it's beyond that, then it will no longer be an effective buffer, all right? And so that's the relative concentration. Then, of course, a buffer will be most effective when acid and base concentrations are high, all right? So what is that? If we define an effective buffer as having this ratio between 0.1 and 10, right? What does that tell us? Well, if we substitute this into the Henderson-Hasselbalch equation, right? The lowest pH that a buffer will be effective is when this ratio is 0.1, right? So that's pKa minus 1. The highest pH in which the buffer will be effective is when this ratio base over acid is 10, right? And so that's pKa plus 1. So therefore, if you have a buffering system with a particular pKa, right, you can adjust the concentrations of the two components to achieve a pH range plus or minus 1 pH unit on either side of pKa, right? So for example, if pKa is equal to 5, right, then with that acid and base system, you can make a buffer with pH range 4 to 6, right? 1 pH unit on either side of pKa. So when choosing an acid to make a buffer, choose one whose pKa is close to the pH of the buffer that you want to make, all right? All right, so here's another learning catalytics question for you. Of course, we're not using learning catalytics, so I'm just gonna pause here again and let you think about this and answer it. Again, if you need more time, go ahead and pause the video, answer the question, and then start it up again. I'm gonna reveal the answer. So which acid is the best choice to combine with its conjugate base to make a buffer with a pH of 4.55? It would be this one, right? So you're basically looking for the pKa that's closest to that number, right? And that's B, right? Okay, what about buffering capacity? A buffer has a capacity to neutralize a certain amount of added acid or added base, all right? And so you can think about this. You have a concentrated buffer which has a lot of weak acid in its conjugate base, or you can have a more dilute buffer, right? A concentrated buffer can neutralize more added acid and base than a dilute buffer, right? And if you add too much acid or base to a buffer, you can destroy the buffer. You can exceed the capacity of the buffer to neutralize the added acid or base. So let's just do a quick example here. Suppose you have 1 liter buffer that is 0.1 molar in acetic acid and 0.2 molar in sodium acetate. So let's think about this for a minute. This buffer is 1 liter. I've kept that just so the numbers are easy to figure out. So I have 0.100 moles of acetic acid, right? And I have 0.200 moles of sodium acetate, the conjugate base, all right? So remember, this neutralizes added base. This neutralizes OH minus. And this neutralizes H3O plus, added H3O plus, right? So the question is, which of these additions would destroy the ability of the buffer to continue to act as a buffer, all right? So will adding 0.05 moles of HCl destroy this buffer's capacity? Well, let's see. 0.05 moles of HCl, that means that's H3O plus, right? I have 0.2 moles of this, so I have plenty of conjugate base to neutralize that 0.05 moles of HCl. So we're fine there. Adding 0.05 moles of NaOH, well, I have 0.1 moles of acetic acid. So we're fine there. It can neutralize that added NaOH. Adding 0.11 moles of HCl, well, let's see. Again, it's going to be neutralized by this. I have 0.2 moles of this, so I have plenty to neutralize all that added HCl. Adding 0.11 moles of NaOH. Oh, wait a minute. I only have 0.1 moles of acetic acid. So I cannot neutralize all this added NaOH, right? So this addition exceeds the capacity of the buffer, okay? All right, another learning catalyst question for you. Go ahead and try to answer that one. Again, I'll pause, let you answer it. Okay, if you need more time, pause the video. So I'm going to reveal the answer here. And the correct answer is D. All right. And again, let's think about it in the same way. I have 1 liter buffer. So I have 0.5050 moles of acetic acid. And I have 0.250 moles of the acetate ion, right? Okay, so if I add 0.05 moles of sodium acetate, oh, I'm just adding more of one of the buffer components, right? So that doesn't destroy the buffer. If I add 0.05 moles of acetic acid, oh, okay, I'm just adding more of one of the buffer components. So that doesn't destroy the buffer. 0.05 moles of HCl, well, that's going to be neutralized by the acetate ion, and I have plenty of the acetate ion, right, to neutralize those 0.05 moles of HCl. So that's not going to destroy the buffer. Adding 0.050 moles of NaOH, oh, wait a minute. I only have 0.050 moles of acetic acid. So if I add that much NaOH, that's going to completely react with all of this, and then I will no longer have a buffer, right? So that destroys the buffer or exceeds the buffer capacity, okay? All right, that's it for today. Next time, we'll start looking at the calculation of titration pH curves. So we'll have that on tap. Enjoy your weekend and enjoy your Monday holiday, and I'll see you all on Wednesday. Thank you.